Hello, water managers and SWIMS users. I'm Russell Errett with the Water Management System Division out of the Hydrologic Engineering Center, and this presentation will be covering HEC-ResSim within SWIMS. This is a multi-part video that covers this presentation, so this will be the first part. And we'll be covering basic concepts within HEC-ResSim and the use within SWIMS for real-time operations. And we'll go through kind of a crash course introduction to HEC-ResSim, what HEC-ResSim is, what it can do, and how we use it within SWIMS. And then we'll cover integrating HEC-ResSim within the CABI, specifically for SWIMS, kind of a brief crash course on how to import a HEC-ResSim alternative into the CABI. And then we'll go through HEC-ResSim for real-time decision making, the reports that are available, plots, standard plots that you look at, also look at doing release overrides that are very kind of specific to the CABI. So looking at the release override editor and the operation support interface. So to start with, let's go through just kind of a brief introduction of what HEC-ResSim is. So what is HEC-ResSim? HEC-ResSim is our software that we use to determine reservoir releases within a river system. So it's kind of an algorithm of rules and constraints that exist within a watershed to operate a reservoir. So a lot of times we use the water control plan to define those rule constraints, and then we operate that based upon some known inflows coming in that we would have from HMS for local flows downstream, inflows to a reservoir to determine an operation that would be suitable for a reservoir. So what can it do? It can determine releases from one or multiple reservoirs. So as simple as a simple headwater reservoir that has very simple rules and constraints to a very complex system that could be multifaceted system operations with multiple reservoirs, either in series or in tandem or both. They can even have several diversions. It can get very complicated. It basically will use a mass balance computation to determine pool elevation and storage, and those are determined from the physical parameters that are put into the HEC-ResSim model for the storage and area curves, and then also the capacity for release from the reservoir. Those are defined in the physical tab, and those are used to determine the pool elevation as it's doing its simulation. Also, HEC-ResSim routes and combines inflows either upstream or downstream throughout the entire routing network so that you can determine what kind of releases or inflows that would come into a reservoir throughout the system. It's a very simplistic routing. There's different types of hydrologic routing parameters. So if you think about this as like an HMS user, you're using hydrologic routing. If you're thinking about it from a RAS component where it's hydraulic routing, that is a little bit more complex. So it's kind of a simplified routing mechanism to route through HEC-ResSim. So looking at a simple HEC-ResSim network, this is what a HEC-ResSim network would look like. So we have reservoirs. So in the reservoirs, you define your pools, your hierarchy of outlets, operational plans. All of that stuff goes into your reservoir editors. And so we'll look into more depth of what those look like. Junctions. So if we're looking at the schematic, these cyan colored or blue colored elements are the reservoirs. This is where all the reservoir elements are going to be defined. So you have 1, 2, 3, and a fourth reservoir within the schematic. The junctions are these red circular areas. So these junctions could have inflows, and you know that there's inflows in there, and there's a white halo around it, so you know there's local flows coming into these junctions. They'll have the outflows computed from them, so they're going to combine the inflow coming in, which will be coming from the routing reach, and any local inflow that gets added to this junction. There's an outflow that comes out of it. And if you define rating curves, so if you want to determine what that stage might be at that gauge, for example, so if you have a USGS stage discharge rating curve, you can define those in those junctions so that you can not only see the flow that's at that junction, you can also see what the estimated stage would be for that junction. And then routing reaches. As I pointed out, these between the red dots, these long reaches here, these blue lines, those are routing reaches. This is where you define your hydrologic routing parameters, whether you're going to use Muskingum, mod pulse, whatever you would want to look at, that will go inside these reaches here. And then also provides connectivity for your routing network. So these can get pretty complicated. So you can see there's routing reaches through here, and then there's also tributary through here. So this is kind of just what a standard HEC-ResSim network looks like. So basically there's a handful of things, but to start with, you have a kind of a guide curve, and a guide curve is just really the target where you want your reservoir. So this could be simply as just the bottom of flood control, so it could be the same elevation throughout the year. It could be seasonally varying, so maybe throughout the year you have a different target for that. But guide curve is basically where ResSim wants the reservoir to be. It's kind of like the goal. So it's always trying to get the guide curve. So that's one key parameter that you want to think about when you're thinking of ResSim. The next thing is the operation part. So generally, whenever they build ResSim models, there's generally should be a basic guide curve operation. And what this is an operational set that only has just basically guide curve. And what that means is anytime the reservoir gets above guide curve, it's going to try to get back down to guide curve based upon physical limits. And what I mean by physical limits is how much can a Tainer gate release, or how much can a sluice gate release, how much can the reservoir itself release per elevation. So based upon the capacity curves that are defined in there, how quickly can the reservoir get back down to guide curve? So that's kind of a physical constraint. Not realistic constraints, physical constraints. And then operating zones. So we start adding operating zones like top of flood control pool, top of inactive pool, and even more complicated zones that it might be in there. Maybe you have 50% pool that might be defined within your water control plan. It has different operating zones. Could be the surcharge zone, the top of surcharge. A lot of times you'll see some reservoir operations have top of dam in there. So there's a lot of zones. There could be several of them. There could be very few, depending upon how complicated the reservoir set is. And then each one of those zones is where you're going to define the rules. So some rules can be applied to all zones, because it may apply to all of them. And some zones may only have one zone that only has a particular rule set in it, because it's the only time that that rule gets applied. So that's the physical constraint of getting the reservoir back to guide curve, and that's what ResSim is doing. The thing that we start to curtail those physical limits are the rules. So this is where we start to make it more realistic to the reality of how we operate reservoirs in the real world. So we start adding rules to that. So the first thing we typically add are release functions at site. So what's the maximum release you can release from a project? What's the minimum release that needs to be released from the project? So that's generally your water quality or your water supply releases that have to come from the reservoir at site. And then we start adding downstream control functions. What are the downstream control functions for that? We don't want to go above this threshold at these junctions downstream, depending upon what zone you are in the reservoir. And maybe we don't want to go below a certain flow. So maybe there's a water supply component to those downstream junctions. And so they can be a minimum or a maximum downstream control function. Rate of changes. These could either be on the reservoir elevation. We don't want the reservoir to rise or to fall. A particular rate of change on the elevation. It can also apply to the release. We don't want to cut back releases too quickly or open up too quickly. So both of these rates of changes can be added to the reservoir. Induced surcharge. This is really associated to a lot of Tainer gate projects. So most Tainer gate projects should have an induced surcharge induced surcharge operation curve. And so this would be based upon pool elevation and inflow. It can be based upon rate of rise. And so those can be defined. Those are generally set for the top of when you're above your top of flood control pool, when you're surcharging your project before it gets to the top of the dam. If you have hydropower, it could be a local system where you're defining, just hydropower at the reservoir itself. There could also be a system hydropower. They get really complicated. Pump schedules for pump back can be added to. Tandem, so there's tandem operations within a system. So if you have one reservoir upstream and has to balance the needs of downstream reservoirs, you can do a tandem operation. There's also system operations too. So not just tandem, but it can also be system where there are parallel systems of reservoirs operating for a common downstream control point, and they can also be in tandem. So it's pretty complicated when you start adding systems. There's prescribed releases and then user scripted. So if out of the box things aren't defined within ResSim, you have the capability to start writing actual code and creating a scripted rule if it can't be defined out of the box. I would caution users to try to avoid scripted rules because they're sometimes hard to troubleshoot if you have issues with them. But that is an option and available. So this is what a reservoir editor looks like. So the physical tab, when we're looking at this, is where we're going to define the physical parameters of the pool storage curve, the outlet capacity curves. But then the operations tab, this is where we're going to set our operation set. So you can see this is an example of an operation set for a reservoir. And then this is a maximum release here from at site at the reservoir. And this is the information provided for it. So it's a pool elevation and it changes seasonally. So we have, this time of year, this is the maximum release rate based upon where we're at in the pool. And then this is a different time of the year. So those can be varying. They can also be very simple. And so the way you're looking at these rules is it's a hierarchy. Obviously, the top rule is the first rule we want to meet. And generally, you always have the minimum release because we want to set those first, and then we start curtailing from there. ResSim is always trying to be the most aggressive to get the guide curve. So we always set the minimum to make sure we never violate that, and then we start capping off the maximums as we start going down. We generally try to add whatever the most constraining thing that we want to add to it to start with. So it's kind of a hierarchy. If you have any issues with these, or moving these rules around might give you some different results as you're working with this in real time. So an alternative. So a ResSim alternative is a reservoir network selection. So we have a run control. So the alternative type is the computational time step. The compute options, those are in your run control tab for the alternative. There's the operations tab. What type of operation set? So you can have multiple operation sets. You can have an operation set for the water control plan. So what the book says. There could be one for water management real time. There could be the guide curve only we talked about. There could be other operation sets. Maybe there's an interim operating plan. Maybe there's a deviation that you generally get for particular constraints. So maybe you want some of those defined. So there could be very different sets of operations, but you set those in your alternative. The look back settings, and we'll kind of cover a little bit more detail what those settings are and what they're set for. And then the time series. So like your local flows coming into your junctions, if there's any look back time series that is needed that you're mapping to your look back time window, or any time series that need to be mapped for external variables. Sometimes some scripted rules require some external variables. So that's where your time series will come into it. And then there's also an additional tab that's not required, but it's in there, is your observed data. So if you're mapping observed to any junctions where you're trying to look at flow or stage, that's where you populate those. So this is what your alternative editor would look like. So again, we went through, there's a run control tab, your operations tab, look back tab. Here's your time series tab where we're populating all the time series that need to go into that network. And then the observed tab I was talking about would be very similar looking to this, but it would be very specific to what kind of observed data you're trying to compare your simulation to. So simulation analysis, there's a specific time window, a set of alternatives to analyze. So that's what your simulation is. So, and there's a lot of tools to look at how to evaluate your simulation. There's plots, reports, there's plenty of reports. You can customize these plots. You can also kind of create some customized reports if you need to. And then the operation support. We'll cover this later on in the presentation specifically, but there's a lot of tools available to analyze the results from the ResSim. And so some of the major features, and we don't cover this, but there's an entire week-long class for ResSim that we offer. And so we get into a lot of the details that go into this, but this graphical system, the schematic, looks very similar when you look at ResSim in its standalone environment, its application. It looks very similar to SWMS. If you're familiar with the WAT, it's also very similar to that. But some of the main things that are in here, you can set a hierarchy for outlet structure, so which structure gets the priority for release first. You can do diversions, diverted outlets. They're smart diversions now. Release allocations, zone-based priorities, computational intervals. You can do 15-minute or anywhere from 5 minutes to 1 day. I think there's even, I believe, 1 month in there. So you can create your time step for simulation in a myriad of different ways. Most SWMS models that have been developed are developed for 1 hour, but those can be very different depending upon your setup for your district and your local region. Customizable plots, reports, induced surcharge operation we talked about, hydropower, again, tandem and parallel system operations, pump back. One of these things that are very heavily used, mostly because a lot of water managers and individuals that have set up ResSim models are very familiar with spreadsheets. So if then else is very heavily used within a lot of models. So you'll see a lot of if then else statements in there. So if these rules apply, if not or else, then this is going to be the rules that apply. We went over scripted rules. State variables is another kind of another variation of the scripts. And then the customizable operation support, which again we're going to cover later on in this presentation. So this rule, what is ResSim's role in SWMS? We're simulating real-time reservoir operations. So ResSim in of itself is used for studies for reservoirs. We use that for risk analysis and for other applications for studies. For our use, we're doing it in real-time operations. So, water management's function is to operate the reservoirs within their region. And this is supposed to help support that. So there are a lot of tools that have been added to ResSim that are very specific to SWMS. One of those things is release overrides and the operation support interface. Those two things, just the concept of a release override is very specific to SWMS. If you were doing a study, doing release overrides is kind of considered a no-no. You kind of have to have all of those rules defined in an algorithm to do your analysis for a study. Whereas in SWMS, we very much want a water manager and their brain power involved with the computational process, which so that override of overriding releases or a pool elevation target is very much integral in this part of it. So that's really the main difference that you would see from ResSim within SWMS versus in a study environment. Generally, I like to say a good ResSim model, if you have a good one, will give you a decent first guess. There are some philosophies that stripping out rules to make ResSim run faster helps out the water manager get to an answer quicker, and that may be true. I do like to add enough rules so that it's giving you a reasonable answer to start with. If it's constantly giving you a release that's well above anything you would do, and it's always doing it for you, I would argue that you probably should add some rules or a little bit more detail to it so it's getting closer to what a water manager would do. So I would try to adjust your rules or adjust the parameters that are in there so that you're doing that. I will say that a study model may take longer to run. So stripping some rules out of there might be necessary to make it efficient for real-time operations. So things of like system operations or very complicated downstream control rules or scripted rules may be taking a hit on your computational time. So maybe it's taking a very long time for it to run. Those are things to consider to remove and maybe try to simplify. Always remember in SWMS we have the opportunity to do release overrides, and that's something we'll talk about here later. So if you have any questions about our software, need some help, or are looking for additional training, check out these links. They can also be found in the description below. Thank you for your time.